Hi everyone, I am Dr.S.SURYA, Assistant Professor, Department of Chemistry, A.D.M. College for Women, Autonomous, NAGAPATTINAM. Today we are going to learn about Coordination Chemistry 2 in 2nd MSc. The introduction of organometallic compound. Organometallic compounds are a class of compounds that contain a metal atom bonded to an organic group. They play a crucial role in catalysis, organic synthesis and material science. Then organometallic compounds are chemical compounds which contain at least one bond between a metallic element and a carbon atom belongs to an organic molecule. Even metalloid elements such as silicon, tin and boron are known to form organometallic compounds which are used in some industrial. The catalysis of reaction wherein the target molecule or polymers or pharmaceuticals can be done with the help of organometallic compounds, resulting in an increasing in the rate of the reaction. Generally, the bond between the metal atom and the carbon belonging to the organic compound is covalent nature. That means when metals with relatively high electropositivity such as sodium and lithium form these compounds, a carbonic nature is exhibited by the carbon which is bound to the central metal atom. For example of the organometallic compound wherein carbon belonging to a benzene molecule bond with chromium is illustrated above. A few more examples of this type of compound are Grignard reagent, tetracarbonyl nickel and dimethyl magnesium. The structure of organometallic compound. The organometallic compound exhibit a wide range of structure including monomeric, dimeric, polymeric. What is monomeric? Monomeric means single metal atom bonded to a organic groups. Then dimeric, two metal atom bonded to the organic group. Then polymeric means multiple metal atom bonded to the organic groups. Then property of organometallic compounds. A few property of organometallic compounds are listed below a short point. The bond between the metal and the carbon atom is often highly covalent in nature. Most of the organometallic compounds exist in solid state, especially the compounds in which the hydrocarbon groups are aromatic or have a ring structure. Then the compound consisting of highly electropositive metals such as sodium, lithium are very volatile and can undergo spontaneous combustion. In many cases, the organometallic compounds are found to be toxic to the humans, especially the compounds that are volatile in nature. These compounds can act as a reducing agent, especially the compounds formed by a highly electropositive metals. From the points given above, it can be observed that the property of organometallic compound differ from the other based on the properties of the metal that constitute of them. Then bonding modes in organometallic compounds. The metal-carbon bond in organometallic compounds can be classified into several types including sigma bond, pi bond and delta bond. What is meant by sigma bond? The sigma bond means formed by the overlap of metal and the carbon atomic orbit. Formed by overlap of metal and carbon atom orbital. Then pi bond formed by the overlap of metal, d orbital and carbon b orbital. Pi bonds formed by the overlap of metal d orbit and carbon p orbit. Then the delta bond formed by the overlap of metal d orbital and carbon d orbital. The organometallic compounds features unique bonding between metals and carbon containing ligands. This section divides into capacity which described how many atoms in a ligand bind to a metal and various bonding modes like pi bond and sigma bond interaction. Understanding these bonding types is crucial for capturing of organometallic chemistry. We will explore common ligands metal carbon bonds and specialized interaction like acoustic bond, connecting this concept to the broader study of organometallic structure and bonding. Then classification of metal carbon bonds is classified into several types, including sigma bond, pi bond and acoustic. The sigma bond metal carbon bond formed by a sigma bonding. Pi bond is a metal carbon bond formed by a pi bonding. Then acoustic means metal carbon bond formed by the interaction of metal atom with a CH bond. That is the difference between the sigma bond, pi bond and acoustic. Sigma bond formed by a sigma bonding and pi bond formed by a pi bonding, and acoustic is a bond formed by the interaction of metal atom with a CH bond. Then binary metal carbonyls. Then binary metal carbonyls belongs to a class of compounds where metal atoms are complexed exclusively with carbon monoxide ligands. These are perhaps the simplest metal carbonyl. Features direct coordination between the carbon monoxide and a single type of metal center. For instance, nickel tetracarbonyl represented by the chemical formula. Nickel tetracarbonyl is the best example of the binary metal carbonyl. It is a classic example of binary metal carbonyl consisting of a nickel atom bound to 4 carbon monoxide molecule. Similarly, iron pentacarbonyl comprises a single iron atom coordinated to 5 CO ligands. Understanding the binary metal carbonyl is fundamental as they serve as the stepping stone to more complex carbonyl structure in organometallic chemistry. Notably, the nature of the metal carbon monoxide bond in binary metal carbonyl has extensive application ranging from the catalyst in industrial process to important intermediate in synthesis. Then cluster metal carbonyl. Then moving beyond the similar binary system, cluster metal carbonyl are fascinating compound comprising the multiple metal atoms held together not only by metal carbon monoxide bond but also by the metal bond. For example, dicobalt octocarbonyl. So, is a notable example where 2 cobalt atoms are bonded to each other to 8 carbon monoxide molecules. The structure is characterized by a variety of bond modes, including terminal and bridging atoms. Then cluster carbonyl provide deep insight into the corporate effect of metal center in bonding in catalysis. These compounds play significant role in industrial chemical reactions, such as the hydroformylation process that are valuable in the study of metal cluster chemistry. The mixed ligand carbonyl introduce an array of complexity into the metal carbonyl chemistry by involving additional type of ligand along the side carbon monoxide. It's not just about CO anymore, but a combination of varied ligands bridging diverse reactivity and functionality to the table. The prime example would be complex, which includes the carbon monoxide ligand, 1 nitrosyl and 1 triphenylphosphine ligand bound to the manganese center. These additional ligands can significantly alter the electronic and steric property of the compound, enabling them to serve the specialized role in catalysis and synthesis. Such mixed ligand carbonyl are particularly important in how much of understanding different ligands and the influence the behavior and property of the metal center, thereby extending the versatility of the metal carbonyl in various chemical applications. The bridging carbonyl represent the unique subclass of metal carbonyl compound. These are characterized by the carbon monoxide ligand that act as bridges connecting to 2 or more metal centers. This bridging mode introduces a fascinating aspect of bonding and reactivity and significantly impact the compound overall property. An illustrative instance is found once again in dicobalt octacarbonyl, where some of the CO groups bridge between cobalt atom and reinforcing the metal-metal interaction and stabilizing the complex structure. Then bridging carbonyl are not only a pivotal in constructing intricate the metal in framework, but also play a crucial role in mediating communication between metal center in catalytic process. Studying bridging carbonyl helps us gain valuable insight into multi-metallic cooperative effect and their implication in advanced materials and catalysis science. Then importance of organic compound. Organometallic compound play a crucial role in various fields, including catalysis, organic synthesis, and material science. In catalysis, the organometallic compound are used as a catalyst in various reactions. Then the organic synthesis, the organic metal compound used as a reactant in the organic synthesis. In material science, the organometallic compounds are used in the development of new materials. Then synergetic effect in organometallic compound. What is meant by synergetic effect? In metal carbonyl compound, CO ligands donate its electron pair in vacant d orbital of metal through sigma bond, and metal also donate its electron in vacant antibonding orbital of CO ligand. This is known as the synergetic effect. And compound refers to the stabilization of lower oxidation state of metal through a interaction of the metal center with ligand. The explanation of synergetic effect. The mechanism of synergetic effect, the combination of two types of interaction. First one is the sigma donation and second one is the pi back donation. First, sigma donation means the ligand donate electron density to the metal center through a sigma bond. Then pi back donation means the metal center donate electron density back to the ligand through a pi bond. What is the difference between sigma donation and pi back donation? Sigma donation means electron density donate a ligand to the metal center through a sigma bond. The metal center donate electron density back to the ligand through a pi bond. The stabilization of lower oxidation state. The synergetic effect stabilize the lower oxidation state of metals by reducing the metal electrophilicity and increasing the metal nucleophilicity. First, reducing the metal electrophilicity means the electron and sigma donation from the ligand reduces the metal electrophilicity, making a more stable in lower oxidation state. And increasing the metal nucleophilicity, the pi back donation from the metal center increases in nucleophilicity, making it more reactive and stable in lower oxidation state. What is the difference between the reducing and increasing metal electrophilicity and nucleophilicity? Reducing the metal nucleophilicity is a more stable lower oxidation state. Increasing metal nucleophilicity is a more reactive and stable lower oxidation state. The example of synergetic effect, metal carbonyl complexes and organometallic catalysts. In metal carbonyl complexes, the synergetic effect is responsible for the stability of metal carbonyl complex such as nickel compound and iron compound. Then organometallic catalysts, the synergetic effect play a crucial role in the stability and reactivity of organometallic catalysts such as Wilkinson catalyst. Then importance of synergetic effect. The synergetic effect is essential for the stability and reactivity of organometallic compound and has significant implication for catalyst and material science. In catalyst, the synergetic effect play a crucial role in a design of efficient catalyst. In material science, the synergetic effect is essential for the development of new materials with unique properties. Then organometallic compound can be classified into several types based on the nature of the bond, metal carbon bond. Then sigma bond, pi bond and acoustic. Sigma bond, metal carbon bond is formed by the overlap of metal and carbon atomic orbit. Then pi bond, metal carbon bond is formed by the overlap of metal d orbit and carbon p orbit. And acoustic means MC bond is formed by the interaction of metal atom with a CH bond. Then 18 electron rule. The 18 electron rule is a guidelines used to predict the stability of electrometallic compound. It states that stable organic metallic compound should have 18 electron valence shell. It can be applied by counting the number of electrons contributed by the metal atom, ligand and charges. In metal atom contribute its valence electron and ligands, each ligand contribute a pair of electron and charges and the complex is also taken into the account. The classification based on the 80 electron rule. The example of organometallic compound classified based MC bond and the 80 electron rule. Sigma bond, pi bond and acoustic. Sigma bond chromium compound with the best example of sigma bond. Pi bond is iron compound and acoustic 16 electron of ethylene. Then bonding in metal olefin complexes and metal acetylene complexes and metal allyl complexes. Introduction of metal olefin complexes are formed by the coordination of an olefin, that means alkenes, to a metal center. The bonding in these complexes involving the donation of electron density from the olefin to the metal center. Then the bonding in the metal olefin complexes involves the overlap of metal d orbit with the olefin pi orbit. If this result in the formation of the sigma bond between the metal and the olefin. The example of result salt is an example of metal olefin complexes. The bonding result involves the coordination of the ethylene molecule to the platinum metal center. And metal acetylene complexes formed by the coordination of acetylene molecule to the metal center. The bonding in these complexes involves the donation of electron density from the acetylene to the metal center. Then bond between the metal acetylene complexes, triple bond complex. The bonding in metal acetylene complex involves the overlap of the metal d orbit with the acetylene pi orbit. This results in the formation of sigma bond between the metal and the acetylene. Then the metal allyl complexes is formed by the coordination of allyl group to the metal center. The bonding in the complex involves the donation of electron density from the allyl groups to the metal center. Then the bonding between the metal allyl complexes involves the overlap with the d orbit with the allyl pi orbit. This results in the formation of a sigma bond between the metal and the allyl group. The low nuclearity carbonyl cluster and 2,3 metal atoms. For example, magnesium, cobalt and iron. The magnesium is a dimanganese decocarbonyl complex with a manganese-manganese bond. Then cobalt is a dicobalt octacarbonyl complex. That means the carbonyl complex is 8. That means so a dicobalt octacarbonyl complex with a CO-CO bond. Then iron, a triferric decocarbonyl complex with a iron bond. The high nuclearity carbonyl cluster, the tetrasium decocarbonyl complex with a triple bond formation. Then rhodium decocarbonyl complex with a 16 molecule of rhodium bond. Then iron rhodium decocarbonyl complex with a iron triple bond or tetra bond. Then stability generally increases with the number of metal atom and the carbonyl ligands. Then Ward rule. Structure based on polyhedral skeleton structure and electron pair theory of Ward rule. The introduction of polyhedral skeleton electron pair theory. Polyhedral skeleton electron pair theory is method used to predict the structure of metal cluster, including carbonyl cluster. This theory states that the metal atom in a cluster form a polyhedral skeleton and the electron pair donated by the ligand occupy the vacant of the polyhedral. The Ward rule is the set of guidelines used to predict the structure of metal cluster. The rule states that the number of metal atom in a cluster related to the number of electron pair donated to the ligand. Ward rule can be used to predict the structure of carbonyl cluster. The application of Ward rule to carbonyl cluster. applied to carbonyl cluster by counting the number of electron pair. How many number of electron pair to the donate the CO ligand? For example, in the cluster, each OS atom donate the 2 electron pair and each CO ligand donate 2 electron pair. Using that rule, we can predict that the OS4CO12 cluster will have a tetrahedral structure. Example of carbonyl cluster following Ward rule: tetrahedral structure, octahedral structure and tetrahedral structure. Thank you.